1.5c, and here we have given the equation ut plus x ux equal to x. So we observe that here we have coefficient in front of the spatial derivative. So we have a velocity that that is not only constant. So we know that characteristics, they will not just be straight lines. What I say now is what you also will know when you have solved some of these equations. And then in addition, we see there is also some additional complexity in the sense that on the right-hand side, there is a source term, an x-dependent source term. In general, we can have a source term here that depends on both x and t and also the unknown variable u. But the method we use to deal with it, to solve it, is the same. So let's also add what we need more is some information about the initial data, u, x, t equal to 0. I prefer to give this a name. I call it, as we have done before, phi x. But also we note that this has, we have been given the information that this should be cosinus 90 multiplied by x. But it's only in the final step that when we have computed a solution in terms and expressed it by means of the initial data phi. After we have done that, then we can replace phi by this specific choice. So we know that this, to compute the solution, involves 2 steps. First, to compute the characteristics, and then we just need to identify what is the equation for the characteristics. The characteristic dx of t. Well, we know it should be dx dt equal to, and then we look at the coefficient in front of ux and observe that it is x of t. Then we must specify what is the starting point for our characteristic. And it's easy to solve this. We use separation of variables like this. And we integrate with respect to time. We integrate from 0 to some time t, and regarding x, we integrate from x 0 to some x of t. That are the corresponding positions in x. And well, I don't think we need to do all the calculations. We will find that this will give us x of t is equal to initial point x0 multiplied by the exponential function with argument t. And then it's always useful to make a plot of what is such a characteristic, what does it look like in the xt space, because the characteristic lives in the xt space, and if we now choose a point, initial point x0 here, and then we will make a sketch of our path, then we see that this will grow exponentially fast with increasing time. So it should look something like this. But then we also note that if we start with an x0, which is negative, we see that this will give rise to a similar exponential behavior, but now we have a negative sign, so it will take the same form, but in negative towards left. So it means that when we walk along this characteristic, we move quickly to the left. When we start at a positive x0, we move exponentially fast towards right. So this is the transport involved in this equation, seen or considered from the characteristic point of view. But now we want to use this characteristic to identify the solution. So we consider the method here consists of studying u along this characteristic. More precisely, we take the time derivative of u restricted to the characteristic. And when we carry out the differentiation here, we first have to take the derivative of the first argument. But then according to the chain rule, we have to take the derivative of x, which is x. Then we also have to take the derivative of x with respect to t, plus the derivative with respect to the second argument. Then we use the equation for the characteristic, namely that which tells us that dx dt is equal to x plus ut. And as usual, the mechanism involved is, of course, now that we identify that this choice of this equation for the characteristic ensures that we have produced the left-hand side of the equation itself. And this is according to the equation equal to x of t. And let's see what happens now. What should we do next? Perhaps I could bring forth this question here for you. What should we do next in order to obtain an equation we can solve? Because here we see clearly the effect of the source term. If we have no source term, then we just produce 0, and it's easy to integrate this equation. We just have that the time derivative of u is equal to 0. So we just have to, we can directly conclude that u x of t is constant. But what is the next step now in order to obtain an equation to solve? Any suggestions? I hope you can hear me. Can just one of you confirm that you still are with me?
So we are with you.
Okay. But let me continue then. Here is our x of t. Well, the point is that we actually have computed and found an expression for x of t, the characteristic. It's over here. So we can simply insert this expression here, which is x0 et. So that means we are left with this problem to solve. And again, we can use separation of variables. We just put all the u-dependent terms on the left-hand side. On the right-hand side, we have x0 et dt. And then we integrate this. This expression with respect to time, we integrate from 0 to t. And the corresponding limits in terms of u is u x t equal to 0, t equal to 0. But this is clearly nothing but initial data, phi, and evaluated at the starting point of the characteristic x0. Here we have the upper limit is u of x of t. And what comes out of this is u x of t is equal to the initial state phi of x0 plus. Now I just moved this limit here, or the effect of this limit here, over to the right-hand side. Then we have to integrate this integral, evaluate this. x0 is independent of t, so we can take it on the outside. And then we have the exponential function and just take into account the limits from 0 to t. Which will give us this expression. x0 multiplied by exponential function of t minus 1. There is one more step to take here, because we don't want to have x0 here. We want to have only as well as in the argument of phi. So we have to observe that x0 is the same as x of t multiplied by the exponential function with the argument minus t. And now we can insert this. So the conclusion is that the general solution for an arbitrary point x and t is that it is phi x e minus t plus x e minus t e t minus 1. We may write this as phi x e minus t plus x. And then we combine, take this exponential function, combine it with the expression in the bracket and get 1 minus e minus t. And finally, we can now also insert the expression for phi, because we have been told that phi of x is the cosinus of 90 with argument 90 multiplied by x. So this is the same as cosinus of 90 multiplied by x e minus t plus x 1 minus e minus t. And then what is always a good exercise is to verify if this solution we have found here really satisfies the equation. So we can compute derivatives and insert in the left-hand side of the equation and check if we then produce the correct right-hand side. So perhaps we can do that. And now I focus on this formulation of the solution. So first, when we look at the situation at t equal to 0, we just insert t equal to 0 and find that gives us phi of x multiplied by 1 plus x multiplied by 1 minus 1. And clearly that is equal to phi of x. Then we want to test if this is the solution of the equation itself. So we compute first the derivative of u with respect to time. Then we first have to take the derivative of the first term. That will give us that is the time derivative of phi plus, and then we have to take the time derivative of the second term. And note that clearly in the general solution, x and t are independent. As a method to derive the solution, we consider a path x that depends on time t. So then there is a clear relation between x and t. They are interrelated. But in the general solution, there is not. So here, when we take the time derivative, x will go on the outside, and we have to take the time derivative of 1 minus e minus t. Let's carry out this differentiation. Here we have to use the chain rule, and we produce the derivative with respect to its argument multiplied by the time derivative of its argument plus x, and then we can take the time derivative of this. The 1 here would disappear, and we have a minus here, and then we take the time derivative of this exponential function, and that will produce another time negative. So what comes out of this will just be e minus t. Now I have to carry out the differentiation of this term, and that will give us minus 1 e minus t. Okay, that was the time derivative. Then we compute ux. That will give us, perhaps we can do this more. Okay. So that will give us, again, a derivative of phi with respect to its augment. Then we take the spatial derivative. And the second term, it only involves x. So the derivative with respect to x will just give us 1 minus e minus t. When we draw the conclusion here, we see that we have phi derivative e minus t plus 1 minus e minus t. Somewhat complicated expression here, but let's see what happens when we try to check or formulate the left-hand side of the equation. So ut plus x ux, that is the left-hand side of the equation, and this is minus x e minus t phi prime plus x e minus t plus, and then we have x that should be multiplied by ux, and that will give us x e minus t phi prime plus x minus x e minus t. So let's hope that this will give us a good result. We first observe that clearly this term is the same as this, but with opposite sign. So that looks good. And similarly, we have produced x e minus t, and we also find this term here with minus in front of it. So what remains is only x. So that looks really good. So we can conclude that this is okay, as well as the initial data. So then we have proved also by verification that our solution satisfies this equation. Any comments to this? Okay, let's also take a look at, I would like to take a look at let's try to obtain some understanding of what kind of behavior is associated with this solution. Let's try to state it here. U x of t equal to, let me write it with this general initial data x e minus t plus x1 minus e minus t. There are a couple of things we can do here to try to get some understanding. We can, what we will do next is to plot by means of a simple MATLAB script a solution at different times. So what we will do, choose t1, for instance, a specified time, and plot u x for this fixed time. And please note that this will be a plot of u as a function of x. And this is different. There is a tendency that students, they will mix up this plot with this plot of the characteristics. The characteristics are in xt space, but the plot of a solution for a fixed time will be will typically be x along this axis, and then u x for some time t1, for instance, along the second axis. So we will demonstrate this very soon using MATLAB. But now a question, an interesting question is, what happens with the solutions with u x t as t becomes large? Then we have to find out what will happen with the argument here, x e minus t. What will be the limit of this as t go to infinity for any x. Well, this will grow or tend or move, converge towards 0. So that will give us 0. And what will happen with this? Again, we see that the exponential function with negative minus t will converge to or go towards 0, so that will converge towards x. So we see that u x t will tend towards phi evaluated at 0 plus x. So it will be equal to the linear function x plus some constant. So that can be good to have in mind when we are going to plot the solution for, and where we also choose time t to be quite large. That is one point. And the other point is that here, when we look at the solution here, we should ask also ourselves the question, where is the effect of the source term? And where is the effect of the equation itself? And if we have solved some of these equations, we will see that this part, which involves phi, that comes from the left-hand side of the equation. Whereas the second term x multiplied by 1 minus e minus t is an effect of the source term. Okay, let's make a plot or run a MATLAB script. You can find the script in the folder related to this week's lectures, and it bears the name EX5C. And here we use the fact that this phi is a sinus function, and we plot it from minus 25 to plus 25. The red dashed line is the initial data, and then the blue solid line is the solution after a small time step. Let's see, what is the time step here? 0.1. So we can ask the question, what kind of transport effect takes place here? Well, if we look here on this, if we look what happens in this region, we see that there is clearly a transport compared to the initial data. There is a transport towards right. This front wave has moved towards right, and you can see the same behavior if you go to the next peak here. There clearly is a displacement towards right, and it becomes stronger and stronger for larger x. And that amounts to if we go back and take a look at the characteristic, this amounts to transport along this characteristic. And then similarly for a negative, when we are on the negative side of x-axis, we will expect to see a similar behavior, but in the negative direction. And that is precisely what we see here. If we look on, for instance, in this region, we see that there is a similar transport towards left, and it becomes clearer as we go further to the in the negative direction. Okay, so this is the transport mechanism. It's not so easy to see the effect of the source term, but let's take a larger time, t2, and then plot the solution. And this will give this kind of waves. And what we can see here is this maximum peak is a little bit higher, and that is typically what we should expect from a source term. It will add something, and we can observe it as an increase here in the height of this wave. And when we look on the left-hand side, we see that there is an a lower value, and that can be understood as a consequence of the fact that if we look at the source term, it involves x, which means that for positive x, we add something. For negative x, we have a negative sign, so it removes something. So let's plot the solution for a larger time, and here for a very large time. And here you can recognize we see that solution O essentially is a straight line, and this straight line is nothing but x, and and since phi, it is x plus 1. So this line here is x plus 1. So in this way, it's very useful to plot the solution and visualize what is the effect, what is the transport mechanism, and what is the effect from the source.
Sir?
Yep.
Sir, so what about stability? Now, what I have understood from stability is that the solution and the initial, so the blue line and the red dashed line, as time increases, they should be near each other. So this is stable. If not, if the solution as it is in our situation, it further shifts to the right, so it means it's not stable. So is it right or this is different?
Yeah, that's a different issue, because stability is something. I mean, what we observe here is the dynamics of the solution. But when we talk about stability, then it's more a question about what happens with the. Then we typically compare two different solutions. For example, Stability with respect to initial data is one issue. Consider phi of x as initial data, and that gives a solution u x of t as we have plotted here. But then stability, if we add some small epsilon, that will give rise to a new solution. And stability, that is a question about, can we control the difference between those two solutions? Can we somehow estimate the difference between these two solutions? More precisely, if we make the difference with respect to initial data small enough, if we make this epsilon small enough, can we control how far away these two solutions are from each other? That will be a study of the stability properties. But what we have studied here is the behavior of the solution itself. So this is not directly related to stability.
Okay, thank you.
But that's an interesting question. Okay, let's. if there are no other questions here, and I see that well, it's the time is 9, so I suggest that we take 15 minutes break, and then I continue with 2 other exercises.